Afternoon, ladies and gentlemen. We'll make a start for our final session of the day. So we're going to hear from three small businesses who all have developed innovations to help decarbonise industry. So I'm going to invite our speakers onto the stage in a minute, I'm going to invite them on now, actually. Guys, do you want to come on stage? So we're going to start the session today with Sean Sargent. Sean is CEO of Green Lithium, and his startup is working on powering electrification with low-carbon lithium. So Sean has been CEO of Green Lithium since 2021. He's a maritime civil engineer. He was previously site director at Berkeley Nuclear Power Station. He spent much of his career at Jacobs before joining Green Lithium. Sean, over to you for the first presentation.
So good afternoon, everybody, and thank you for taking the time to listen to us. So you'll see fundamentally Green Lithium, it's all about enabling low carbon, sustainable electric revolution. So this is the electrification of transport and trying to produce battery chemicals, in our case, lithium chemicals for electric vehicle batteries in a low carbon, sustainable way. So I'll start with a bit of a brief description. It's quite a short presentation because I'm hoping to give you some time to ask some questions at the end, but fundamentally, the whole concept is around bringing lithium-bearing minerals from around the world. We're a merchant refinery, so we can work with any mine, and we'll bring those minerals to the UK, to our refinery. We've got a refinery itself, which uses a modern 21st century process. It's very different to the process that's used for the way that lithium chemicals are refined in the world today. And then we'll sell those chemicals that we produce to the cathode producers, so the people who make the positive end of the cell. Lithium is a key component of the cathode, and then once it gets put into the cathode active material, they then go on to the gigafactories. So you've got these long new supply chains, and our market is the European market. So at the moment, these supply chains largely don't exist, and we're all about bringing in localized production to support those new supply chains. We'll build 2 lines in Teesside. We've got room for 3, but the initial plan is to build out 2. That will produce about 50,000 tons per annum of battery-grade lithium chemicals. And to give you a sense of the context, that's about 1.2 million electric vehicles per year. But actually, when you look at the European market as a whole, it's a tiny proportion. Given that there's no lithium production in Europe as we sit here today, that's only 6% of the projected demand by 2030. So you can get the sense that actually we're just a small drop in the ocean compared to what's required. And I think in many ways the electric transition is full of mountains that need to be climbed. And I think that's what makes it so exciting. So I thought I'd give you a very brief overview so you can understand what we're doing around decarbonisation, so you can get a bit of context around what it is. So there's 3 primary parts to our process. The first one is calcination. This is where you bake the rock through large rotary kiln ovens, and this is required to make the rock soluble. So in its naturally occurring form, it's not water soluble. The second part of the process is hydrometallurgy. So instantly you realize it needs to be soluble, otherwise it's just not going to work. So we bake the rock in large kilns. There's a high gas demand associated with those kilns, and that's where a large part of the carbon footprint comes from. So that was one of our primary focuses. The hydrometallurgy phase is all about hot water, as you can imagine. So again, it's got a very large electrical demand. It's got a very high steam demand. So the steam can potentially come from gas-fired boilers, or it can come from electrical heating. But again, electricity is the second large input that has a significant impact on our carbon footprint. And then the third stage is crystallization. So once you've produced, in our case, a liquor that's very rich in lithium hydroxide, you then have to kind of put it through this evaporation process that concentrates it again, until you get to a monohydrate salt, which is the raw material for the cathode active material. So again, a large amount of electricity required for those evaporators. So in very short order, there's obviously a long form of this, but to give you a picture of how we decarbonize that industry. So straight away, I mentioned the process we use is different. We don't use the acid leach process that's very commonly used, primarily in China, but also in Western Australia. We've gone with an alkali leach process, and straight away that gives you a dividend of about 25%. It's lower temperature, lower pressure. It's much more selective about the chemicals it dissolves out from the ore, so it targets the lithium, and it means you don't have to spend a lot of time then purifying the liquor to get it down to that high concentration lithium hydroxide. So that lower temperature, lower pressure, straight away the energy demand's lower. We get a 25% reduction on the carbon footprint. One of the huge dividends comes from using renewable electricity or a low carbon electricity source, because it's such a power intensive process. Being able to reduce the carbon footprint by selecting where we get our power from. And we selected a site in Teesside that's got really good access to lots of renewable energy projects. And we're doing some work at the moment to decide what's going to be the best power mix to supply the plant. Clearly wind, solar are all great candidates. We're also looking at nuclear power as a potential using small modular reactors. The next bit, again, it's a very large proportion of the carbon footprint for the refinery itself, is being able to swap out that natural gas for hydrogen. And in Teesside, we benefit from suppliers who are participating in the government contract for difference scheme, so they're agreeing a strike price. And what that means is we'll have access to high volumes of low-cost hydrogen almost from the start of production. Our plan is to have our refinery operating pretty much from the start of 2027, and that's aligned with some of the projects who are planning to produce blue hydrogen in Teesside. So that's one of the most exciting aspects. And there's not many places in the world where you can get that sort of access to high-volume, low-cost hydrogen. So it's a big enabler for us. Of course, the ultimate goal, you get another reduction in carbon again by moving from blue hydrogen to green hydrogen. So the great thing about Teesside, there's lots of people also thinking about how you can produce green hydrogen on site. So it's another chunk taken off that carbon footprint. The last bit, so all of that takes you to about 75% reduction. And most of that we can achieve within the first few years of operating the plant. The last 25% is the hardest. It's the bit that's going to be the most challenging. So it's dominated by scope 3 emissions. So it comes from our raw materials, transporting those raw materials to the site. It comes from the carbon footprint of the electricity supply, if there's any residual carbon footprint. And that's the bit we've tried to buy ourselves a bit more time. So our commitment is to be net zero by 2035. And it's by working with suppliers who have already got plans for reducing their carbon footprint, the miners who are looking at using renewable power sources to enable their plans, that will get down to that 100%. There's just one last aspect I'll mention, which I think is actually on the next slide. So the plan is to do it sustainably too. So you can imagine if you ship 10 tons of a concentrate across from, say, Western Australia to the UK, a question I get asked a lot is, well, only a ton of it's ending up in lithium-ion batteries. Why did you bother shipping the other 9 tons across the planet as well? Well, it's really important to make the point, and it's the middle point here. We don't see, if you're producing batteries and producing a waste form, then you're not doing it properly. You've got to do it sustainably. You've got to have an eye on making sure that anything you produce has got a downstream market, and yet you can use circular economies to reuse that material. So we're working with the University of Sheffield. We're looking at taking the byproduct, which is sodium aluminium silicate. It's an analcime sand. It's got sort of slightly pozzolanic properties, which begins to hint at what applications you might use it for. It sort of acts a bit like a cement, but of course you don't have to bake it like you do cement. It's already in a form that can be used. So we're looking at a number of products we can potentially use that material for, and make sure we can reuse every ton of material produced by the process. The top one's equally important. So today we mine material out the ground, we convert it. That's where the first generation of batteries are going to come from. They'll be used in cars for 15 years or so. Then they'll look at second life applications. So there'll be further applications of those, the batteries, grid storage, domestic storage, but eventually they'll reach end of life. And what we're doing is we're working with a number of battery recyclers to understand how are they going to capture the lithium from those recycled batteries. And there are some emerging trends there which are quite exciting for us. It means that the lithium is going to come out as a midstream salt, and we're making sure our process flow sheet's got the ability to re-refine those salts, back to battery grade lithium hydroxide or carbonate. So having that circular economy is increasingly over a period of time going to be an important part of our feedstock. And of course, when you're refining it the second time round, the carbon footprint drops dramatically because you don't have to do that heavy pyrometallurgy phase at the beginning. And then finally, using good process design to minimize discharges, minimize emissions. It's a zero liquid discharge process, so all the liquor is recycled again and again through the process to make sure nothing comes out into the drain at the end of the process. The same is true of gaseous emissions. We have to make sure that we control. One of the challenges of moving to hydrogen from natural gas is you produce a lot of nitrous oxides. You've got to make sure that's controlled and have an efficient burn process to minimize the gaseous emissions, because you have to scrub them and remove some of those chemicals to be compliant. So all in all, you put all that together, you end up with a process that is low carbon, increasingly low carbon over the next decade, but is also sustainable. There's nothing we produce that ends up going to for waste disposal. Everything can be reused and we can find applications for. At that point, I would welcome any questions, assuming I've still got time.
The mic working. There we go. So we've had a few questions that have come through. So you mentioned Teesside as the site for your location. I mean, are you feedstock neutral in terms of green versus blue hydrogen? I mean, this morning we heard from industrial clusters and you know, the HyNet cluster, the Humber cluster. It's interesting how you chose Teesside for your location. Is there anything you can sort of expand on the reasons why for that? That'd be really interesting.
Yeah, I think, I mean, Teesside for many reasons. It's a deep water port. We can import those raw materials effectively. We're right by the container terminal, so we can export our product to all the major European ports where the battery clusters are likely to be, pretty much with 24 hours notice. Equally important, it used to be a big steelworks, so there are people there who are used to baking rock and understand the challenges. It would also used to be a very large petrochem facility on the Wilton plant, so that means we've got a pool of human resources of people with all the relevant skills. We just need to update those to 21st century jobs and skills for pyrometallurgy and hydrometallurgy. But you're absolutely right. The thing that absolutely clinches Teesside is the industrial cluster. The fact that you've already got in tow, you've got contract for difference developers producing blue hydrogen plants, so we almost certainly will start with blue. We do think there's a dividend to moving to green over a period of time, so we're keen on that too. But that decarbonisation, the carbon capture facilities that are available are definitely large enablers for a large industrial plant like this.
Thank you. We've had another question that's come through. So how does lithium compare to hydrogen? So I suppose interpreting that, you know, how does hydrogen compare with battery technology, compare with electrification, in your view, in terms of energy transition, how we reach net zero?
I refuse to be drawn on this subject. I think almost every technology that enables electrification of transport has got a place, will find a place. The technologies will develop and emerge. I personally think hydrogen's got a long way to go in terms of powering electric vehicles. You can see particularly in the larger vehicles there's some benefit to that, as are sodium-ion batteries. But the market's so big, there's such a big challenge, and we all want it to be successful. Without successful electrification of transport, then Paris climate change commitments are meaningless. So we think there's a place for all of it. We think lithium-ion is going to be a very enduring part of that, and it will be a significant part of that solution.
That's great. And one more question, if you don't mind. I'm particularly interested to hear the answer to this. So how much of battery material is recyclable?
Today or in the future?
Both.
Okay. So there's the European Battery Directive, which is legislation that's been brought in that insists that if you're going to sell an electric vehicle in Europe, you've got to make sure that the batteries can be recycled. So today, I would say the track record's not excellent. I think a lot of the batteries that are being produced today, although they're a route to getting to that point where they're more recyclable, they're quite hard. There's definitely examples of batteries and the technology required to recycle them. I think if you spoke to a battery battery recycler 2 years ago, they'd have been talking about black mass, and they wouldn't have known what to do with it after that. Today, you speak to recyclers, they're talking about hydrometallurgy processes, they're talking about leaching processes, they're talking about solvent extraction processes. And that means, for us, that means you can save the lithium. In early recycling, the lithium was often destroyed, but I think progressively, certainly in the timescale that this ramp up in production is going to occur, recycling is going to become a very, very significant portion of the industry.
Great. Thank you very much. Thank you for your very insightful presentation.
Thank you.
So our next speaker is Dominic Vergine, CEO and founder of Monumo. So Dominic is a serial entrepreneur, having founded 4 businesses during his career, a social enterprise and also a charity. So I'm really excited to hear what you've got to say, Dominic. Over to you.
Thank you. Thanks, everyone. Thanks, Innovation Zero, for putting this on. So I'm going to talk a bit about AI for engineering. I'm going to do this in the context of electric motors, which is where we're focused. But actually, I want to bring out a bigger topic here, which is how disruptive and how powerful AI in engineering is going to be over the next decade, because I don't think it's being talked about very much at the minute, and it's going to be really, really significant. So you can kind of swap out the word the electric motors there for any other piece of engineering, and I'll try and explain why. So what do I mean by best? So I mean best in every conceivable way. I mean better efficiency, better recyclability, cheaper. So let me put some numbers to this. So 3, 4, 5,000 off the price of an EV, 20, 30% more efficient, 50, 60% lighter. I mean, big numbers in terms of the improvements we can achieve. So how do we do that? Well, we are looking at every possible solution, and engineers haven't been able to do that before. You cannot explore every conceivable way of solving a problem until now. Now, we can't quite do it yet, but we will be able to do it in the next decade. And I think this is hugely positive and exciting for achieving a zero carbon world, because essentially we will be condensing what might have been 100, 200 years of gradual product improvement and iteration, hopefully down to 10, maybe even 5. So that is what we're able to do now. And that is a very, very, very long way from what we do as engineers today. Now, this is not being critical of engineering or engineers at all. It's simply that nobody lives 1,000 years and can study every single part of a system and understand it sufficiently to put it together as optimally as possible. But what we can do now is use this technology to solve global problems. So the key point here is this: we are going to be able to do things and see things that are well beyond current human ability. Why? Because in exploring the huge design space that is enabled through the data that we can collect through machine learning, we will find new opportunities, new ways of designing motors, new ways of putting things together, new ways of creating energy generation, clean energy that we have not seen before. So I equate this a little bit to a lot of scientific discovery where things are found through accident. So something strange happens, and then the people working on it will think, well, that's interesting. Why has that happened? And then you dig into it and you find something that is then really groundbreaking. And what we can do is use AI, use deep tech, to actually unearth those things, find them deliberately. And that will mean we can really accelerate the development of crucial technology. So I'm talking about AI, but really the fundamental thing here is machine learning and deep tech. So 80% of what we do is making things really, 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 really fast. And the faster we can make the simulation, the faster we can explore the space, the more we can do, the more kind of prototypes, the more avenues we can explore. Now, if you're in an engineering company today, you can't just go down some avenue to see what happens, because it takes months, and it takes resource, And is there any gold at the end of that tunnel? Who knows? But we can do that virtually. So we can do things that would never otherwise happen. But 80% of it, as I say, is all about machine learning and speed. The big thing is this vast design space here. So, that is, essentially it's trillions and trillions and trillions of prototypes done virtually. And that allows us to evolve optimal solutions. And this is not about replacing engineers. We still need the same number of engineers. It's about getting much, much better tools so that we can condense that sort of evolution process. So you think of the internal combustion engine, it took about 100 years to get from the starting point to its ultimate solutions, which were the common rail diesel, the 4-cylinder injection engines that most cars had. Look at EVs today, scattergun. There's no consensus around what motor to use. Most of them are using permanent magnets. That's not sustainable. So we need to go much, much faster than the 100 years we did before. So this is actually out of date. So we can now run 500,000 simulations in 2 days, and by the end of the month, probably, if we pay for the cloud compute, we'll run 1 million in a day. Now, the current engineering companies, the tools they are using are rooted in 90s tech. So there's all sorts of layers on them, and they're very complicated. They can, in theory, do lots of things, but they are not based on the CPU. They're not based on the latest tech. And so this is what really can empower all of us to do much, much, much better, not just in motors, but in actually any aspect of engineering. So what's happening here is this shift. And if we thought the shift from analog to digital was amazing and disruptive and quite scary, this is much, much, much more. We haven't really even started to see, I would say, both the positive and the negative implications. But the positive ones are enormous. All AI is it's our latest tool. And it's mainly not AI anyway. It's not actually intelligent. It's mainly about massive computing speed. And we can use that well as humans, or we can use it badly, or we can use it incompetently. And probably we'll do a bit well, a bit badly, and most of it incompetently. But if we just move the needle slightly towards using it well, then that's how I think we will actually achieve a sustainable world. And what will happen, just the same as before, giant companies will vanish. Companies we've never heard of before will appear. Bill Gates has said 8 to 10 Tesla-sized companies will emerge from clean tech, from what we're talking about here today. But they will do that by using these new tools. And the sustainability potential is absolutely enormous. So I can never quite believe this figure, but I keep checking it. Is it there? No, so the mining waste point there, every ton of permanent magnets creates 20,000 tons of mining waste. That's because the magnets aren't rare. They're all over the world. It's just they're very thin. So if you want to get a lot of them, you have to dig a lot up and then condense it down. And then this isn't sustainable. So that's just one example. So there's huge potential here to make everything we're doing much, much more sustainable if we use these new tools wisely. So at the moment, everyone is talking about AI writing essays. Now, it writes essays very, very quickly. Quality of the essays, they'll get better. They're pretty good. It's very impressive, but it's all about speed. But the output is something that we can do perfectly well ourselves. The output is an essay or a painting that badly imitates Van Gogh. These are things that people do very, 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 very well. However, what we don't do very well is kind of come together and understand people from all sorts of different disciplines. And this is kind of a macro version of looking at engineering. If you look at a plane, it's made up by, I don't know, probably 100, maybe 200 different expert disciplines. We're good at becoming experts. We go deep on a subject, but nobody can go broad and deep. And that's what this technology will allow us to do. It'll allow us to build the depth and then do the breadth. And I actually started out by thinking about the the Sustainable Development Goals, the 17 global goals, whilst I was working at ARM, the semiconductor company, and I was thinking that AI could help us solve the goals. Now, unfortunately, we are several decades away from that, but the point is that in order to find the sustainable solution, one group of experts, one domain, will have to understand that they can't reach 100%. They can't get to the level they would like because it actually has a negative impact on something else in the system. And we are so bad as humans of lifting ourselves up and looking down and thinking about these things. So we need this kind of technology to help find the optimal route, because it will mean some people compromise and some people have to do a bit more, and something may seem more important than the other, but that's how to find the optimal point, and that's what global sustainability will be about. So next decade, I guarantee our use of AI in engineering, which is fundamentally about physics and maths, so probably computers will be quite good at it, it's going to be very exciting to see what products emerge. Thank you very much. Any time for questions? Or?
Yes, we've got a few questions. So the first question, so AI is very often involved in optimization and detailed design, but a lot of the challenges we face in engineering are building things at scale, at a bigger scale, you know, rolling out carbon capture networks at a scale that's never been seen before. So how can AI kind of work on that other end of things where we need to develop things at a bigger scale to help us achieve our net zero targets?
So that's not my area of expertise, but I mean, it is all about scale. So what computers are very good at, let's say, is doing things very, very quickly with huge amounts of data. And so navigating that is going to be the important thing. I think that AI is already proving useful in processes, but the next thing we will see is it being very useful in terms of actual physical design of products.
And a couple of sort of broad questions here. So given the complexity of engineering problems, how can we ensure that the data quality fed into machine learning is sufficient to prevent major design flaws?
So that's a very good question, and that is where you've got to work in partnership with the human engineers. Those deep domain experts need to be in the teams with the AI and the ML, and that's a tricky juggling act, because what you don't want to do is insert all of our bias into that system, because if you do that, then you won't find the new things. But at the same time, you don't want the system producing things that have design flaws, or maybe cannot be manufactured. So it's a balance. But I think from what we've seen, the opportunities that come out are immediate. They're actually quite easy. You know, when you see them, it's things like a waveform that would be optimal for a motor, and so the motor team tell the rest of the engineers, we need this waveform. But then that waveform's not optimal for the battery. But nobody looks at that because it's never been co-designed. But when you look at it, you're actually, okay, the performance of the motor goes down slightly, but the battery performance goes up very significantly. And so when you see it, you think, oh, right, well, we'll do that then. But it's only through these systems that you get shown those opportunities.
Thanks. And one final question. So I think we're all quite familiar with, you know, the exponential growth in computing power and, you know, sort of seeing those graphs and things. I mean, how do you think AI will develop over the next few years? Will we see that sort of exponential rise or slowly take off? I mean, what's your view on that?
I think we'll continue to see it grow. I think the next jump will be if and when we get quantum computing working, then that's obviously another, you know, step change in speed. But fundamentally, all of these things are all about the speed we can do things, because once we teach AI the laws of physics and the right laws of maths, then we'll be the faster we can explore all the different potential, the faster we'll come up with optimal solutions for everything we need. Thank you.
Thank you. Thank you, Dominic, and thank you, everyone, to the questions there. A round of applause, please. So I'd like to welcome our final speaker on stage today. We have Aidan O'Sullivan, from Carbon Re. So a similar topic around AI but for material decarbonisation. So Aidan, over to you, please.
Thank you very much. And yeah, it's great to be on a panel where there's such a through line of ideas. And I think there was a question on scale, which I'll address in my presentation as well. But yes, we're Carbon Re. We're a startup founded from Cambridge and UCL University, and we're focused on decarbonising heavy industry. So this is Innovate Zero. So obviously the reason we're all here is we're interested in the energy transition, and the question relating to scale is really important to consider when we're talking about the scale of the challenge. So in terms of the trajectory that we're on, we're heading towards 59 gigatons of CO2 emitted in 2030, which is leading us to about a 3.5 degree C world. And where we want to be is a 1.5 degree C world, which is carbon emissions of 25 gigatons per year. So the delta between these scenarios is huge, and if you look at the scale, putting those numbers in context, the impact of COVID-19 on the world was only about 2 gigatons. So in terms of what we need to achieve, the scale of the challenge is massive, and also the time to do so is really limited. So in terms of solutions that move the needle on climate change, they need to have two characteristics. They need to have speed, and they need to be able to scale. So we need to look at solutions that, when scaled globally, will achieve gigatons of impact. And we also need to be able to implement them very quickly. So latest IPCC report is calling for very quick cuts in emissions globally. So that's what we need to achieve in terms of where we're at. And again, this is, you know, an innovation conference. So this graph on the left here should be familiar to some people. It's about technology learning rates and how that evolves over time, how we get better at different technologies. So obviously renewables are part of the solution. They're very much involved in the decarbonisation of the power sector, and electrifying transport will then decarbonise that sector as well. But if you look at the slopes of these axes, it's showing the decrease in costs for these technologies as we install more and more of them over time. So this is known as the learning rate. So as we double the installed capacity of solar, the cost of building solar comes down by about 30%. For offshore wind, it's about 10%. For nuclear, the learning rate goes the other direction, which is a bit of a problem and down to regulation and why there's such interest in small modular reactors. However, for software technologies, the scaling is completely different. So this is from Hugging Face. This is an open source community that releases large language models. And in 1 month, when the latest model was released, it was available or downloaded 29 million times. So the laws of diffusion and scaling for software technology is completely different than hardware. You know, you don't have to worry about, as soon as the latest wind turbine is available, it takes about 20 years to propagate through the fleet. However, software, as soon as it's improved, there's immediate release and it can scale globally. So if we look at how that's worked with, you know, a recent example, GPT-4 had 1 million users in 5 days. So as a technology, artificial intelligence embodies some of the characteristics that we need in terms of solving climate change. So what do you do about that? Well, you found a AI company that at its heart is focused on achieving gigatons of carbon emissions. So start a company that is entirely focused around that, but using AI. So in terms of how we started, we're a collaboration between the Cambridge Institute for Manufacturing and the AI lab at UCL. And we've been backed by climate tech investors, Planet A, who are a German investor, and Clean Growth Fund, who are here today. So again, entirely motivated around the use of AI for achieving significant impact. And what we want to do is attract the best AI talent in the world, which is why we're based in London, in order to build multidisciplinary teams to focus on this problem. So now that you have this ethos, where should you look to deploy AI? Where's the kind of area where you can have the most impact? So if we look at carbon emissions, one major source of emissions that hasn't really been tackled is the energy intensive industries. So again, there are solutions for electrifying, you know, transports, renewable generation, aviation, things like this. However, the hard to abate sectors have really not been touched very much. We've talked about carbon capture storage and hydrogen, and these are kind of being treated as silver bullets. However, the scale of opportunity here is really significant when they're responsible for about 20% of global emissions. So there's a huge opportunity in terms of scale there. If you can move the needle a little bit there, it has a large impact. And again, these are really essential industries. So these are materials that we need for the functioning of society. We need cement, we need steel, we need ceramics, we need glass. That's not going away anytime soon. However, we need to think about how we manufacture them and how we make them for a net zero world. So what can we do with AI to start to drive this process in a different way? So what we do is we try and help operators see the future. We try and take this process, which is reactive, and make it predictive. So the scale of manufacturing here is incredibly large. This is a rotary kiln, the type that Sean was talking about in terms of lithium manufacture as well. And what essentially happens here is temperatures are raised to about 1500 to 1600 degrees to induce the chemical reactions that transform the material into what we need in a product. So tons and tons of limestone go in, and tons of fossil fuel get burned, because again, it's a very energy dense fuel that you need to achieve these high grade levels of heat. And because of that, the opportunity for improvement is really significant. So what typically happens is an operator controls the plant from a control room, which, as you can see, is quite complex. The process itself is very complicated, but it is, because it's quite dangerous, it is a closed system. So what we do is we use AI to simulate that process, to simulate potential actions and solutions, and we recommend these to the operator as to how they can run the plant a bit more efficiently. So in terms of giving you a kind of example of how that might play out, so what we do is model the process really well, and then we use an AI agent to look at what's going to happen, look at the current settings in the plant, and to try and move the operator in the direction that improves the overall energy intensity or the amount of energy per ton of material created. So in this way, it's really aligned with what the customer is trying to achieve, because again, it's driving down their fuel costs while also maximizing production. However, we're also able to predict the material qualities as well. So it's really important when you're doing this that you don't reduce the quality of the material. It's a key constituent, and that's essentially what we're trying to use AI to do, to model the changes in the material process and to make sure we're always above that quality threshold of making good quality cements or good quality materials. So there's a huge opportunity in the process because of the scale of things. Again, optimizing the fans in this process mean you're pulling in liters and liters of air in order to induce combustion, and you want to be right at the level where you're only bringing enough air in to achieve combustion, and then not heating up and releasing cold air back into the atmosphere unnecessarily. So again, the whole process overall is incredibly complex. Operators are being asked to do things that are really challenging on a day-to-day basis. Their inputs are changing, their requirements are changing, and what we have tried and built is a tool that supports them in this act. So it's currently been tested in plants. So we have had a successful trial deployment where we were shown the capability of the tool to reduce energy consumption by about 9%. And this translates directly into fuel cost savings, because it's optimizing the amount of fossil fuels they're using, which then reduces carbon emissions. So because these are really low margin industries, which is why we focused on them, a small change in their fuel consumption leads to much bigger profits as well. And again, because of the scale, we were able to reduce about 44,000 tons of CO2 into the atmosphere by doing this. So this is quite significant at just one plant. So I think 10 cement plants is equivalent to all the cars in London, I think, in terms of carbon emissions. So this is what we've been focused on. This is what we built. It's a human-in-the-loop solution. So what we do is we take data from the plant. Again, we have to set up a live data feed from the plant so that we have a continuous update of what's happening. We use this to develop a model. So again, as Dominic was saying, we take all this physics and chemistry data and we train an AI to learn the relationships in there, build a digital twin, and then help it optimize the process for the operator. So it allows it to pull certain levers and to induce and then give these to the operator through the dashboard in terms of what he should be doing to make the process more efficient. So that's where we are currently. So we're an AI for climate company, and we focused on product as a way to have impact. But in terms of where we're going overall, what we've developed so far is focused on cement, but it's all based around the pyro processing process. So this is any process that has really high grade heat is something we're interested in doing. So that's steel, that's glass. We have active research projects funded by Innovate UK and UKRI, exploring developing our tool for that as well. And in terms of the future, where we're going, as Dominic has pointed to, simulation capability is incredibly important. So what can you do once you have an AI that's learned across 50 cement plants, 50 steel plants, 50 ceramic plants? You've got something that's basically learning material sciences from the ground up. So the opportunity there is, incredibly large. It's a kind of a AI for science opportunity that we're looking at, where we'll be able to look at how we make materials from the ground up again. So this is Carbon Revolution, and yeah, thank you very much for your attention today. Have I time for questions? We're also in the booth across the way if you want to come for further questions if you run out of time.
So we've got a question that says, how long did it take to build your cement digital twin? I suppose just adding on to that, industry is quite a traditional sector. How easy are you going to find it to start working with, the 78 high emission sites in the country to actually kind of penetrate and take it out of the lab and actually get it to be deployed in industry? Is that an easy thing to do?
So we're already out of the lab and deployed in 3 locations around the world, Vietnam, Spain, South America. We've done a project in India as well, and we're looking at other opportunities soon in places that are very large in cement, like Turkey. It's interesting because there is this all-pervasive understanding of AI now. Everyone knows what AI is. So when you talk to engineers in a cement plant, you don't have to explain the concept to them, and they're technical people. They want to try new technology. So while it is a traditional industry, we are also surprised at how we're pushing on an open door a little bit in terms of new technology. And what was the first part of the question again? Sorry.
So how long did it take to build your digital twin?
Well, we're constantly getting better and getting faster at doing it. It depends on the data quality and how the issue's there. Again, one of the reasons why we've built a really multidisciplinary team is a lot of computer scientists themselves don't have experience with this kind of data. Say they're more used to computer vision problems or natural language processing, whereas we're very focused on data from industrial processes, which is very niche and very particular. So we've got physicists, chemists, engineers, all working together to build something really impressive. And the short answer is it's getting faster, but it took us quite a while to begin with, and we're constantly iterating on that.
That's great. We've got quite an interesting question here, philosophical question. So what about digital footprint? There's a lot of energy involved in running things like this. I mean, people have heard about Bitcoin and things like that being the energy consumption of whales annually. I mean, how do you ever how do you see that? And
yeah, it's a really great question. I guess a lot of data centers are taking care of that by buying carbon credits and by committing to using zero carbon energy as part of what they're doing. So again, Google have done that as well. But yeah, the idea for us would be that the emissions that we save dwarf what we're doing in terms of electricity costs. And again, we see electricity kind of going to zero carbon a lot faster than heavy industry.
Nice. Okay. Thank you very much. That's the end of our questions. Can we have a round of applause, please, for all our panelists? And as this is our final session of the day, I'd like to thank all of our speakers today, all of our moderators for hosting their interesting discussions. I hope you've enjoyed the conference and all the sessions. Thank you to all our speakers who've graced us with their presence and their knowledge today. And I'd like to thank every single one of you here for turning up and being part of the event. So that is the end of the Industry Forum today. Thank you.